Hello everyone, I am Huanqu, a PhD student from the University of Sheffield. I'm glad to present my research work here. My topic is Analysis and Mitigation of Demagnetization Issue in Stator slot PM machines. The presentation is divided into 5 parts. Stator PM machines have some advantages over rotor PM machines. Easy heat dissipation when forced cooling is employed, and easy PM retaining and robust rotor structure. Stator slot PM machines have one more advantage, which is fault tolerance under the uncontrolled generator operation. Fig 1 shows the machine topology of a stator slot PM machine, from which we can see the magnets are placed in the stator slot, and they are magnetized in circumferential direction. The adjacent magnets have opposite magnetization direction. To explain the working principle of stator slot PM machines, simplified model is employed, as shown in Figure 2. At open circuit condition, the magnet flux circulates within the stator, and there is no back EMF. When the armature winding is excited, the stator core becomes saturated and the PM flux is forced into the air gap under the rotor. The amount of the PM flux forced into the air gap and rotor depends on the armature field strength and the stator core saturation. Then the magnetic field of the PM is modulated by the salient rotor and eventually induces effective back EMF in the armature winding. Then the demagnetization is checked under heavy load condition. One is pure ID is injected in the armature winding. Another is pure IQ is injected in the winding. Figure 3 shows the demagnetization ratio contour, and which is defined using this equation, where BR0 is the pre-demagnetization remnant flux density, and BR is the post-demagnetization value. When pure IQ is injected, the demagnetized area is distributed at one corner of the PM facing the air gap. When pure ID is injected, the field by the armature reaction is used to weaken the PM flux, and the demagnetized area doubles. From Figure 3b, we can see both PM corners facing the air gap are demagnetized. In Part 4, different methods are employed to improve the demagnetization. First is to adjust the stator and rotor tooth width. As can be observed from Figure 4, when the rotor tooth width is 3 mm, the demagnetization area is very small, and demagnetization ratio is also negligible. Rotor tooth selection will influence the torque performance significantly. As shown in Figure 5, the torque is decreased by about 30% when rotor tooth width is 3 mm. Similarly, when changing the stator tooth width from 1 mm to 6 mm, different demagnetization ratio contour is presented. When the stator tooth width is too large or too small, the magnets are more easily demagnetized. When it's too large, the reluctance for demagnetizing field is small. When it's too small, the PM length in magnetization direction becomes long, and the demagnetizing field becomes strong. When the stator tooth width is around 3 mm, the demagnetization area is very small, and the torque is decreased by 40%, which is not cost-effective. The second method is to shape the magnets or the rotor tooth. Figure 8 shows how the magnets are shaped, and the magnet shaping is defined by two parameters, delta x and delta y. Figure 9 shows the influence of delta y on demagnetization when delta x equals 2 times delta y. When delta y is increased to 0.2, 0.4 mm, there is no demagnetization, and the torque performance is not affected. However, the manufacturing cost will increase. The tooth shaping is defined by the parameter R. As can be observed from Figure 12, increasing the parameter R will improve the demagnetization. However, the magnets are still partially demagnetized even if R reaches maximum value of 3.2 mm. Increasing R will reduce the torque due to the increased magnetic reluctance. The third way to improve the demagnetization is to introduce tooth tip, and tooth tip investigation is considered into 3 scenarios. The first is to consider the width of the tooth tip as 0 and change the tooth tip height. As can be observed from Figure 15, when the tooth tip height becomes larger and the magnets are better protected from the demagnetization. And when tooth tip height is around 0.5 mm, there is no demagnetization. The torque performance is not affected by the PM position, and the slot area is only reduced a little. The second scenario is to put the magnet over the tooth tip, and the tooth tip is defined using H-tip and W-tip. From Fig 18, we can see that increase of tooth tip height can help to ease the demagnetization, which is similar to the first scenario, and increase either tooth tip height or tooth tip width will increase the PM flux leakage and hence decrease the output torque. It is worth mentioning that tooth tip width should be selected as a small value to maintain the output torque and reduce the demagnetization risk. Meanwhile, the tooth tip height should be selected properly to avoid demagnetization as well as minimizing the torque sacrifice. The third scenario is to put the magnets between the tooth tip, and 5 tooth tip shapes are considered. The first is when the PM thickness equals to the tooth tip height, and the tooth tip is defined by two parameters, W-tip and W-tip2. The second tooth tip is shown in Fig 20b, and the demagnetization in Fig 20b can be predicted from Scenario 1 and Fig 20a. Similarly, the demagnetization condition in Fig 20c and d can be predicted from Fig 20a. And the tooth tip shape in Fig 20e is defined by the parameter R and W-tip. From Fig 21, we can see that when the tooth tip is shown as Scenario 3a, the magnets are at risk of demagnetization, no matter what the values of W-tip and W-tip2. The increase of W-tip and W-tip2 will reduce the output torque, which is due to their influences on magnetic reluctance and modulation effect. Fig 23 shows the influence of the parameter R and W-tip on demagnetization in Scenario 3e. By properly choosing the parameter R and W-tip, the demagnetization of PM corners can be improved significantly at the cost of output torque. Generally, The increase of R will increase the magnetic reluctance and hence decrease the demagnetized area and reduce the torque. The change of W tip will influence the magnetic reluctance and the PM usage at the same time. If this technique is employed alone, it is not easy to eliminate all the demagnetized areas without decreasing the torque significantly. Some conclusions can be drawn. The rotor-stator tooth width optimization can help to improve the anti-demagnetization capability, albeit with a significant torque reduction. PM shape can prevent the demagnetization problem without affecting the torque. However, the manufacturing cost is increased. The influence of tooth tip is discussed into three scenarios. The best one is to move the magnets slightly away from the air gap without using tooth tip. Thus, this is the best method to protect the magnets from demagnetization without sacrificing the torque and cost. Thank you.